Now, in the previous test of the acrylic, we did not crush it all the way to failure for a couple of reasons. One, that MTS-10 only goes up to 10,000 pounds, and secondly, we took the shield off so it wouldn't hurt anybody. Now we're going to bring it over to the 60,000 pound machine. This is a hydraulic machine, so it doesn't work with servos and stepper motors and screws. It works with a big hydraulic press. Literally 60, 70-year-old machine, but a pound is a pound is a pound. This works on several different scales. You can see the low scale, I can't quite see that number. The medium scale, I think it goes up to 24,000 pounds. And remember, it's still a 60,000 pound machine, but we can change the sensitivity of that needle. And now Rahul has switched it all the way over, so it's on the 60,000 pound scale. The black needle that's not moving indicates the load. The red needle that Rahul is moving just follows the black needle. So the black needle kind of pushes the red needle along. And what that allows us to do is keep track of the maximum load. Remember, this is 60-year-old technology. So that valve there releases fluid to flow into the cylinder, and that valve allows the fluid to come back, and then there's a switch that operates the hydraulic pump. So the fluid then, when Rahul opens the valve on the right, will flow, through out of the pump into the cylinder down there, and then it causes the table to move up, right? So as opposed to the other machine, and this one, the crosshead up there stays fixed, whereas the table moves up and down. So for compression, we're actually going to push the table up. Now Rahul is explaining what's going on there. The crosshead is actually movable via those screws, and so what he can actually do is just push the control electric motor, which just raises the crosshead up and down. But once that crosshead is in place, it no longer moves. There's that acrylic specimen that we deformed somewhat before. It's plastically deformed, but now we're going to set it on a piece of steel there. We don't want to set it right down on the table. Steel we can replace, the table we can't. And you can see there's been some compression tests that have damaged the upper platen already. That's not good. So to make up for that, we're going to put another piece, kind of a washer, an intermediate piece between the acrylic and the crosshead. Remember, in this case, we're going to push up with the table rather than push down. So you can, normally what we would do is put the shield around it, put the intermediate piece down, and then compress it this way. But to give you a little better view, we're going to take the safety measures off. Don't do this on your own. And then you notice the guys are wearing safety glasses, face shields, and they've got the cameras protected. Just in case. So he's going to set that piece as centered as he can. We don't want anything to pop out sideways. So he loads that up. And they're deciding which way to set it on there. And so now what Rahul is doing is he's using the electric motor to lower the crosshead down to the specimen, making sure everything is really nice and centered. And this is not a terribly scientific test; it's more for a demonstration. Hence, we only have one 60,000 pound machine. And now he's going to take a look at the. He's got it on high scale, so the scale goes all the way up to 60,000 pounds, which means like each quarter circle is 15,000 pounds. I'll put the follower all the way down there. And then while Rahul is watching the scale here, I think either Ed or Dave will be lowering the crosshead. Those are the valves. So right now he's opened that up just a little bit, right? So now that allows fluid to flow from the piston back in, so that there's no way we can raise or lower the table because we're just allowing the fluid to flow right back out of the piston. And they're going to lower that table until we start to see just a little bit of load, and that way we know it's touching. I mean, it's too close to eyeball, so we're actually going to lower it down. You can see the precision of this instrument, plus or minus 50. There the load rose a little bit, which means that we have contact. Now I think Rahul is going to fire up the pump. And so now we're circulating oil from the, the power end of it, the pump, into the piston, but then we allow it to flow right back into the pump. So it's just making a big loop, like Rahul is showing here. And then what Rahul is going to do is close the return valve. That's what you're looking at. There he is closing the return valve until it just barely touches. You don't have to slam the valve shut. It just barely closed. So now he's going to open up the supply valve and start supplying some valve to the piston. What happens when the supply valve opens? We're pushing fluid into the piston. It cannot come back, so the only option is for the piston to move up. And it takes a little bit for all the air to leak out, and the system bleeds a little bit. We haven't run this. In quite a while, since I think last fall. So there might be some air bubbles that have to bleed their way through. And we're going to watch this carefully as soon as we see the load start to increase. Once it starts to load up, we're going to switch over to the close-up view, and the machine noise is going to get pretty loud. So in a few seconds, I'm going to stop talking. In about 30 seconds, I'm going to stop talking, and we'll just watch. But keep in mind, every quarter circle on that dial is good for 15,000 pounds. And we still don't have any motion. Maybe Rahul's going to give it just a little bit more oil. No, he's going to hold steady where it is. Now we're starting to see some motion. The load is increasing. We're already up to 2,500 pounds. It goes fast. Fluids are incompressible. Up to 5,000 pounds already. And here comes the noise. Holding steady at 7,500 pounds. That's about 1/8 of the scale of a quarter is 15,000, so that's about 1/8 of the scale. You can see the certification sticker there. It has been calibrated, despite the fact that it's 60 years old, 70 years old. It has a current calibration. And you can see that the hoop stresses, the circumferential stresses are actually in tension, even though the bulk of that specimen is in compression. Some extra safety measures around the cameraman and the camera. So if you think about this, it's roughly doubled in diameter now, which means the circumference is doubled. But if you think about it in terms of area, the area of this thing has gone up almost as radius squared. So what kind of stresses are there now? It's very, very complicated when the deformations get large. Small deformations are easy. These large deformations are very complicated. So in different parts of this cylinder, there's simultaneously tension, compression, all different directions of stresses. Approaching 8,000 pounds, it looks like, according to Rahul.
So it's failing soon, right?
You probably wouldn't have expected a brittle material to compress like this because it's not really brittle. Cast iron is a better brittle material for experiments, but cast iron takes huge loads and it's much more dangerous when it fails. Now we're over 15,000 pounds. The stress might actually be lower because the surface area is really huge right now. Much more surface area even though we're at nearly 20,000 pounds. Whoa. This is why you wear safety glasses. So now he's opening the release valve, so that allows all the oil to flow from the cylinder back into the pump housing. It flows back, shuts down the motor. Let's take a look at this fractured sample. Evidence of both viscous flow as well as, and so you can see it failed in tension. It failed in the circumferential direction, and all that stuff shattered out of there, whereas the original compressive load stayed in place.